So we're going to have a look at our three states of matter. So we have solid, liquid and gas. We'll look at the particle diagrams, so how you draw them, and then their properties as well. So first up we have a solid. So a solid, we've got it here. We draw our particles as circles. Now this could be an atom, or it could be an ion, it could be anything. We just draw them as circles. So we have a regular pattern. They are all touching. We say they are vibrating, and we have a strong force of attraction between particles. And they have the lowest kinetic energy. Our solid will stay the same shape and volume. So it has a fixed shape and volume. So it has a fixed shape and volume. So we have a fixed shape and volume. And next up, we've got a liquid. So a liquid, again, we draw our particles as circles. We've got an irregular pattern. So in my solid, it was this regular pattern all in a row. The liquid, they're kind of all over the place, but they are still touching. It's important to note that they are still touching in a liquid. In terms of their movement, they will slide over each other. So they will slide over each other. We've got a relatively weak force of attraction. We've got sort of the middle kinetic energy. I'm not going to write anything there for sort of the middleist kinetic energy. They have a fixed volume, but they take the shape of the base of the container. What we mean by that is that the amount of liquid is always the same, so the volume of liquid. So if you have a water bottle and it's filled up with water and then you pour it into a glass, you've still got the same amount of liquid, you've still got the same volume of liquid, but the shape that liquid will take has changed. Same as if you were to pour it onto the floor. There's the same volume of liquid there, but it's now in a different shape. It's now in a puddle on the floor instead of taking the shape of your water bottle. That's what we mean by when they changed the fixed volume, but they take a different shape. And finally, we've got gas. Oops, apologies there. We've got gas. Our particles are drawn like this. So our particles are not touching. See, I've got them all over the container. They are moving in all directions. So they are moving in all directions. There is no force of attraction between the particles. They have the highest kinetic energy. If you remember from your physics lessons, kinetic energy is the energy of a moving object. Because these are moving the fastest, they've got the highest kinetic energy. And they have no fixed shape or volume. So we have no fixed shape or volume. Means we can put a gas into a very, very small space, onto a very, very big space, and it will fill the entire space. It will change the pressure. Again, there's a bit more physics in there. But think about if you blow up a balloon, you're forcing in a lot of gas particles in the air into a very, very small place. That's why the balloon expands. So those are our states of matter. You need to know how to draw them. Make sure, the important part, with a liquid, you draw the particles still touching, and with a gas, you make sure you fill the entire container. So we're now going to have a look at changing of state. So that's going between being a solid, a liquid, and a gas. And we've got this graph here, and we've got these two dotted lines, say the melting point and the boiling point. So we're going to have a look at what happens with it. So we're going to start with our solid that we've got here. Now I would suggest copying down this graph. Now here they are vibrating. So they are vibrating. As we add temperature, all we're doing essentially is we are increasing the kinetic energy. So we are increasing the kinetic energy. At this point, they start, as they get hotter, they vibrate more. When they vibrate more, they overcome the forces of attraction and turn into a liquid. So we've got a regular pattern, but they are still all touching. Again, we can heat them up again, and they become a gas. At this point here, all over the place. So as they go up, they get more kinetic energy. As they get more kinetic energy, they overcome the forces of attraction. This point here is where we change state. Again, think back to your physics lessons and your latent heat of vaporization and melting and so forth. That is what is happening at that point. So we're going to add on a little note here. So as the temperature increases, the kinetic energy of particles increases until they are, or they have enough energy to overcome the forces of attraction. So they will overcome those forces of attraction and change state. The reverse obviously is true when we get colder. As the temperature decreases, the kinetic energy of particles decreases until they don't have enough energy to overcome the forces of attraction. And we go back down again. So as we go up, we're a solid here. The particles start vibrating faster and faster and faster and faster and faster. I'm trying to show there with the laser pointer. Till eventually they can overcome it and they can move around over each other. They're no longer vibrating, they're sort of moving around in places. As they get more and more energy, they move faster and faster and faster until they can just move wherever they want to as a gas. And these points are known as our melting point and our boiling point. So our melting point is where we turn from a solid into a liquid, and our boiling point is turning from a liquid into a gas. And they may ask you a question in the exam to predict the state of something based on its melting and boiling points. We think about the temperature and we decide where it is based on that. So we're now going to look at mixtures. And we're going to look at, well, first we need to define what a pure substance is. Now, a pure substance is something made of only one type of particle. It's only got one type of particle in there. Now, that particle could be an atom, it could be an ion, it could be a compound, but it only has one type in there. They have very sharp melting points. So when we say sharp, we mean it is precise. So for example, water melts at 0 degrees C, and we know it's exactly at 0 degrees C. Impure water would melt at a range of temperatures. So a mixture has more than one type of particle. I'm going to add on here that they are not chemically bonded. So they are not chemically bonded. And a mixture will melt over a range of temperatures. Now they have different chemical properties. So all these particles have different chemical properties. So that allows us to separate them. So that means we can separate them. Now there are a number of different techniques you need to know about. We're going to go through them sort of fairly quickly, and we're going to have a go at a question for it. So our first one is distillation. So distillation will separate a solvent, that's a scientific word for a liquid, and a soluble solid. So that just means something dissolved in a liquid. Or dissolved in a solvent, we should say. Now what we do is we have our mixture here. So we've got seawater here. This is just salt and water. We would heat it up. Now, as we heat it up, the particles get more kinetic energy, and our ones in our liquid will turn into a gas. So we get boiling happening here. So up here, we've now got gas particles. And as they come through here, we have something called a condenser. This lowers the temperature. So here we will lower the temperature. Therefore, we have less kinetic energy. So we turn back into a liquid. So we have a gas at the start and a liquid at the end. So we start with a mixture of a liquid. We then get a gas, and we turn it back into a liquid, but we have separated them because the salt has a higher boiling point than the water. So we can separate them based on those points there. Next one we have is something called fractional distillation. Now, fractional distillation, very, very similar, same process, but it will separate a mixture of liquids as opposed to just a liquid and a soluble solid. And the most common one is crude oil. I think when we've done the crude oil unit, we look at how we separate crude oil. This is just a simplified version of it. Again, we apply heat, so increase in temperature. And that means an increase in kinetic energy. Up here, we've got our condenser. We decrease the temperature. We get a decrease in kinetic energy. We then separate them based on their boiling points. So they'll go up. Now, this is filled with glass rods. It's called a fractionating column. Now, the glass rods, so the tiny, tiny glass rods there, increase the surface area. And that allows us to make sure we only get the liquid we want evaporating or boiling and becoming the temperature, becoming the gas. So the liquid with the lowest boiling point, right, BP for boiling point, boils first and is removed. And having the thermometer there means we can monitor the temperature at what they're coming out at. So if we wanted to get water out, we need to know we need to have it at 100 degrees. So the temperature is monitored using the thermometer. So our temperature up here is going to be the boiling point of the liquids. So it's going to be our boiling point of the liquids. And we can then separate out all the different fractions of the mixture. Our next one is filtration. And filtration will separate a liquid and insoluble solid. So insoluble means it doesn't dissolve. Now we pour our solution through filter paper. Now our filter paper, and we've got a funnel as well, is a bit like a sieve. And what we have is our liquid particles can pass through, but our solid particles cannot. So our liquid particles pass through. Our solid particles do not. We then, we've got a couple of terms, we'll just refer to them. We have something down here called the filtrate, and what is left up here is called the residue. So this could be used, for example, to separate sand and water. We pour it through, the sand will remain up here, the water will pass through into the beaker. And next one we've got is crystallization. So again, this is very, very similar to distillation, but we don't get the liquid at the end. So we can separate a soluble solid and a solvent. So remember, our soluble solid means that just means that it's dissolved. Our solvent is a liquid. Now we heat this up, and so you heat the solution, and then importantly you leave it in a warm place to crystallize. The reason we do that is we get larger crystals. If we just heat all the water away, we get very, very small crystals. If we leave it in a warm place, we get larger crystals. We then need to scrape the crystals off. And we dry them with filter paper. Or you could dry them in an oven using a bus. A sensible way of drying them, but drying them with filter paper is a nice way to do it. If you're feeling really good, you might even say you pat dry. So you're just dabbing them gently. Our final one is chromatography, and this is separating out a mixture of soluble solids. So it separates a mixture of soluble solids. We've got a couple of things on here. So we've got the setup. We've got our solvent. It is below the start line. We have our start line here, which is in pencil, because ink will run. And then we have our chromatography paper. Now, we've got two phases in this, which come up occasionally. So our chromatography paper is known as our stationary phase because it doesn't move. And our solvent and our solutes are known as our mobile phase. It does move. Now what we will see is that all of these solutions will move up the page. I'm just going to do them into different ones on here. So we've got some different colours. We'll do a red one as well. And then we can see what colours they all contain. So it would move up and you can then work out what things they contain. So for example, this one, substance X, contains part of C and part of A and B because it's moved to the same level. Other thing they might have you do is work out something called the RF value. Now the RF value is just how far it moves up divided by the distance of the solvent front. So our RF value is the distance substance moved divided by the distance the solvent moved. Now, I think they normally give you this equation into the exam. It's always worth doing some questions on it. But as a side note, it will always be less than 1. It's always going to be less than 1. So the final thing is an exam question. And the exam questions come in a number of ways. They might ask you to draw a diagram showing particle models, labelling part of a diagram, saying what equipment is being used, something like a thermometer or a condenser, or they will ask you how to separate things. Now this brings together two different separating techniques that you need to know about. So have a read of the question and we will pause the video and try and answer the question. So you should now only be watching if you've answered the question. So our first bit, labelled diagram, we've got it here. So we have our funnel, paper, and a conical flask. So we've got a funnel. Key part is the filter paper. And then we've got a flask or beaker. The next part is describing how a sample of pure dry sodium chloride crystals can be obtained from the filtrate. That's what would be left in the beaker. And we're going to heat the solution. We're then going to leave it in a warm place to crystallize. And then finally, we scrape the crystals off the container and pat dry with filter paper. Well done if you got all 5 marks on that question. Thank you very much for watching. Take care. Have a good rest of your day. Bye-bye.